All right, everybody. So we're going to move on to something a little different here. And what this is an explanation of some elements that are central atoms that do not follow the octet rule. All right, so far we've seen that the s level and the p level will contain 8 valence electrons when they're full, and that's usually what we see in some of the dot structures that we've seen. But there are a variety of other elements that can bond differently, and we want to be able to explain how and why they do this. So this is the next explanation for this. So again, how do we adjust the model? How do we check on the SPDF model and see if it can be adjusted to or modified to explain some other types of bonding? All right, so we took a look at elements. Now, the problem with this is, and I bring this up with carbon, is if you look at the SPDF model of, and this is a good example to explain it, is if you look at the SPDF model of carbon, all right, it doesn't explain how carbon forms four equal bonds. Okay, now to see what I'm talking about, if we look at carbon's valence shell here, okay, if we look at carbon's valence shell, we will see carbon's atomic number is 6. It's 1s2, 2s2, 2p2. I'm sorry, 2p2. All right. So if you look at the orbital diagram, you'll see it's 2s2, and then there's 2 electrons in the p level. And again, there's a slight difference in energy here. Right. So the 2p is slightly higher in energy, or if you want to think further from the nucleus in that case, than the 2s2. So this is carbon when it doesn't bond, right? This is just carbon by itself. However, when carbon bonds, it has 4 equal bonds. So how do you explain carbon forming 4 equal bonds or having 4 single dots? It must have to have that in order to form the octet where you would have 8 valence electrons around it. But when you look at the SPDF model, when you look at the bonding here in the orbitals, how do you actually manage doing 4 bonds? It doesn't make sense. Okay, so the solution to this is what scientists have realized is that carbon will blend, okay, its S and P, okay, and you can also do this with D. So we're not going to do this yet. We'll do this later on with the D, to form a new set of bonding orbitals called hybrid orbitals. And again, if you recall what a hybrid is a mixture of orbitals, right, or a mixture of things. So if you had a red rose and a white rose and you hybridize those, in biology, in genetics, you would end up getting a pink rose, right? But a pink rose is a new rose, right? It's a new thing that's caused by the blending of the genes. Okay, so again, a new set of bonding orbitals called a hybrid orbital. So the hybrid orbitals actually have a little bit of a different names based on where they came from. Okay, now just to show you, so this would be carbon that would be unhybridized, right? You'd have a 2s2 and a 2p2. So what we're going to do is we're going to take this, what carbon does is it takes one of its electrons from the 2s, okay, and it moves it into the empty box so that everybody has 1 electron, okay? So that's going to become a single electron in the s. Each of the p orbitals is going to have a p, and then we're going to blend all the orbitals together so that there's 4 of them. So 1 from the s, 3 from the p, makes 4. Now, this is where the orbitals came from. So we're going to blend all of those into a new thing called sp3. So each one of these orbitals is called an sp3 orbital, okay, which came from the original. This is where it came from. So basically, a pink rose over here comes from a red rose and a white rose, right? So it came from the pieces, but now is a brand new set of orbitals, okay? So when carbon does this, we're going to say that carbon has 4 sp3 orbitals when it bonds, okay? So these are called sp3 orbitals. Each one of them is called sp3. It's no longer s and p. Okay, so that's called a hybridized orbital. So hybridization is the mixing of the s and p into sp3. Now, if you take s1 and p3, that's going to equal 4. That's going to be the number of orbitals that you have to fill. So you can see why carbon has an empty spot here, an empty spot here, an empty spot there, an empty spot there to fill. All right. So again, what does this look like as far as the electron clouds look like? Okay, interesting is we talked about the s orbital being the sphere. the p orbitals being, so this being the s, this being the p, and the p. Now we're going to mix all of these into each of these sp orbitals. So think about the nucleus now being in the middle, this being one dot, this being two dots, this being three dots, and this being the fourth dot. Again, the nucleus is positive, it's in the middle. And now you can form a bond to this, a bond to that, a bond to that, and a bond to that in a tetrahedron. Okay, where before, how you can do that with the element by itself. Okay? This idea of blending orbitals allows us to expand the ideas of how we bond. Okay, so that's going to become important. So in this chart, so basically separate orbitals. Okay, why do we do this in a way too? Okay, and this is going to become important also later on. Is why this happens is also for energy levels. Okay, for energy. Okay, you have lower energy, more stable bonds, and it allows carbon to form more bonds. Again, what happens when you form bonds? When you form bonds, energy is released. Okay, and that's important to know. So this allows carbon to form the maximum number of bonds, maximum number of stability. Okay. All right. So what does this really help us do? Okay, hybridization will then help us. Okay, to explain the bonding in molecules with central atoms. Okay, that have more or less than an octet. So now we can actually manage 4 electrons, 6 electrons, 8 electrons, 10 or 12. Okay, now again, you don't forget you also have hydrogen that has 2. Okay, so that has 2 valence, but again, that's only 2 valence electrons in one orbital, so we're not going to worry about, hybridizing anything. There's nothing to hybridize, it's only one orbital. So at this point, we'll be able to explain 2, 4, 6, 8, 10, or 12 using this idea. Okay, now, a couple of important points, and these are 4 really important points going forward. Please make sure you review this, go over it, ask questions. Okay, number 1, to find out the hybridization, you want to count the entire total pairs of electrons, bonding pairs, comma lone pairs, and add them together, and that's going to give you the hybridization. Okay, so for example, if I have carbon with 4 bonds around it, okay, I'm going to have a 4 comma 0, 4 bonding pairs, comma lone pairs. Okay, that if I add that together, I'm going to be sp3. Okay, because I have 4 bonds, 3 plus the 1 is going to be 4. Okay, so sp3 would be 4 bonds. Okay, another one, if I have nitrogen, okay, that has 3 bonding pairs and 1 lone pair, okay, that's also going to equal 4. Okay, that's going to be sp3 also. If I have oxygen that has 2 bonding pairs and 2 lone pairs, okay, 2 bonding pairs and 2 lone pairs, that also equals 4. That would also be sp3. Okay, again, we're mixing the S and P levels for these 3 atoms. So just going to show you how you do that. Okay, it's the total pairs, bonding pairs, comma lone pairs. Okay, important to know. If you want to find the shape, okay, we're going to be concerned with the bonding pairs only. Okay, important to know. So if you have sp3, you can have the same hybridization, but again, this would be a tetrahedron because the tetrahedron, right? Because the bonds are tetrahedral. Okay, we can call this pyramidal, all right? Because the bonds are pyramidal, okay? But still sp3. Okay, we can call this bent. What's actually bent? The bonds are bent. So the bonds are bent, bonds are pyramidal, it's a tetrahedron. But all of these have 4 total pairs. Okay, so the shape is from the bonding pairs only. Okay, now a couple of things, and this is going to become important. You may see double bonds and you may see triple bonds. Okay, those are extra bonding pairs. Okay, and they're not going to count towards hybridization for the total. Okay, really important. You want to count single bonds only for the hybridization. Okay, so that's going to be important to know when you look at this. Okay, really, really important. All right, so a good example is going to be maybe, I will give you a simple example as carbon dioxide. If we look at carbon dioxide, in this case, all right, and again, you may have a little question because we didn't talk about double bonds and triple bonds too much. Okay, look at the central atom. If you want hybridization, count total pairs, okay, which is single bonds plus lone pairs. Now you have no lone pairs, but you have two single bonds. So we have two single bonds and no lone pairs, which equals 2, okay? Well, we didn't do that yet, but if it's 4, it's sp3. If it's only 2, then it's going to be sp, okay? sp1, sp1, which equals 2. Okay, so only the single bonds count towards hybridization. Only the single bonds. All right. So we're going to look at that single bonds and lone pairs. Okay. So that I know there's a lot here, and we're going to have to practice going through this. So definitely ask some questions when you go. All right. All right. And last but not least, memorize boron, beryllium, and a hydrogen. Okay. They always want less than an octet. So for example, hydrogen only wants 2. Beryllium only wants 2 pairs. We're 4, and boron will always have 3 pairs, and that's it. So these will always look like this: 2, 4, and 6 total electrons. Okay, so really important. Again, a lot here. I know there's a lot here. We'll have to practice as we go. All right, so in the chart, okay, we'll go through this one at a time really quickly in the chart. Okay, and then again, we're going to be doing this a couple days in school, so you'll get an idea of how we actually, run the show here. But all right, so basically, if we start with hydrogen, the number of valence electrons is going to be 1. Okay, so you'd have hydrogen with 1 valence electron. You're going to be stable with 2, okay, which is going to just be hydrogen with a single bond, okay, which is 2 electrons. You're going to have a linear structure, okay. We're not going to worry about hybridization, so there's none. Okay, with beryllium, okay, beryllium is going to have 2 valence electrons, okay, but we're going to hybridize them and we're going to separate them into 2, okay, which means beryllium wants to form 2 bonds, okay, for 4 total electrons, okay, around the central atom. You're going to be stable with 4, okay, and then that would be sp. Again, you have 2 valence electrons, sp, for 2 total pairs, okay. Boron has 3 valence electrons. We're going to take those dots and we're going to separate them out into hybridization, okay, and we're going to form boron with 3 around it. The shape now will be trigonal planar. Trigonal planar is a flat molecule, 3 bonds around it in this trigonal or triangular shape that is then flat. Okay. Now, if you take the S and P, this will be S, P, and P. This will be S and P. This will be just S. Okay. Now, as you get more and more pairs, now you get to the position where you're going to be the 8 valence electron spot. Okay. So again, you're stable with. So this is the important column here. You're going to be. This is what they have. Okay. This is what you're going to be stable with when bonding. Okay. So important here. Okay. Now you hit the octet rule. So this is the octet rule where we all know and love. It's what we use to the S2P6 thing. All right. So 4, 5, or 6 valence electrons here. So this is going to be. This could be carbon, this could be nitrogen, this could be, oxygen with the dots. Okay, so it's going to be 8 valence electrons. Okay, so carbon can have this, right? Nitrogen could have this, okay? Oxygen can have this, okay? Where you have your bent, your pyramidal, your tetrahedral. Okay, again, this is your 4, 0. This is your 3, 1. This is your 2, 2. This is your 3, 0. This is your 2, 0, right? So this is your code, your bonding pairs, lone pairs. Bonding pairs, lone pairs, bonding pairs, lone pairs, bonding pairs, lone pairs. Notice that these will be sp3 because they all add up to 4. This adds up to 3 pairs. So the total pairs will always be the adding of the subscripts here, the S and the P. So once you get your total pairs, you'll know what hybridization you have. Now, this can be expanded out a little bit. Okay, once you get to period 3, 4, or 5, you then can end up with a D level. And you can use your D level electrons to add extra boxes. All right, and this can happen. All right, so for example, you have 5 or 6 valence electrons. So for example, you can have phosphorus that would expand it out. So instead of having an S and a P, you can also use some D orbitals to do this. Okay, so for example, you can have 10 valence electrons. So phosphorus can have 1, 2, 3, 4, or 5 bonds. Okay, so you can have 5, 0 here. Okay, you also can have sulfur, which you can have 1, 2, 3, 4 bonds and a lone pair, right? And you can even have elements that have 1, 2, 3, and 2 lone pairs. Okay, so you can also have a 4, 1, or you can have a 3, 2. Okay, and again, you would be trigonal bipyramidal. Okay, so trigonal bipyramidal would be this one here. Trigonal bipyramidal is here. This one would be called seesaw. This would be called T-shaped. All right. So again, there's a variety of ways you could do this, and again, you're going to use the D here for an extra box. Okay, so we would call it S1P3D1 for 5 pairs around the central atom. Okay, so this would be trig bi, okay, param. All right. Now, you can also do this with elements that can even expand out even more with 6 or 8 valence electrons. So that's even more. Now we can use D times 2. You can use 2 boxes from the D to get 6 total boxes. All right. So again, you can have 12 valence electrons. Okay. So for example, sulfur can have 1, 2, 3, 4, 5, or 6 bonds. Okay, for a 6, 0, which would be called octahedral. All right. You can have elements that have a lone pair and 5 bonds. So you can have a 5, 1, which would be called square pyramidal. Okay. And then you can also have elements that have 2 lone pairs and 4 bonds. So you can have a 4, 2, which would be called square planar. All right. And again, you would have sp3d2, 3 plus 1 plus 2 is 6 pairs. So here's your pairs of electrons here, your hybridization. Now, I know this looks very complicated. You do not have to memorize all these shapes. I'm going to give you a reference table. Okay, and on your reference table, you will see a reference table on page the correct page here. On page 24 of your packet, there'll be a reference table which outlines this information. And again, I'll allow you to use a version of that reference table on the exam. So I just want you to understand it and be able to note it rather than sit here and have to worry about memorizing everything. All right? All right, so that ends it. We'll do some examples coming up later on. The next thing we'll be talking about double bonds and triple bonds. I just want you guys to hang in there and review it if you have to. All right, we'll see you in a bit.